In this video, we're going to talk about least squares solutions to systems of equations. But before we get into that, let's just recall the main fact that we learned last time, which is that if you have a matrix, any m by n matrix A, then the row space of A and the null space of A have the property that the set of vectors that's orthogonal to the row space of A is precisely the null space of A. And if you apply that fact to A transpose, the row space of A transpose is just the column space of A, and so we see that the column space of A, the set of vectors orthogonal to the column space of A, is precisely the null space of A transpose. And we're going to use this fact, this second one actually, in finding a formula for something called a least square solution to Ax equals b. So what's the least square solution? So sometimes if you have A and B and you want to solve Ax equals b, there's no solution, right? That's called an inconsistent system. We've seen lots of examples of that, so let's just look at an example. Let's say that A is this matrix 1, 0, 0, 1, 1, 1, and B is this vector 1, 2, 3. Well, actually, if you look at these matrices, you can see that Ax equals b has no solution. And one way to see that is that whatever x is, if you do A times x, because in this first column you have 0, 0, in the second column you have 1, 1, whatever A times x is, that result, the second and third components have to be the same. And when you look at B, the second and third components are not the same, so Ax equals b has no solution. You can also just, if you're not convinced by that, just do the Gaussian elimination and you'll see that there's going to be a problem. So we cannot solve Ax equals b. However, what we can ask is, which x makes A times x as close as possible to b? In other words, what we want is a vector x that minimizes the distance between Ax and b. And an x that satisfies this, we'll call it x star. So such an x, we'll call such a vector x, x star. Well, let's take a look at a picture. So let's call this first column A1, and let's call that second column vector A2. So what's happening is, in terms of the picture, so here's the origin, here's the x-axis, the y-axis, and the z-axis, the positive x, y, and z-axes. A1 is 1, 0, 0, so A1 is this vector. That's A1. And then A2 is 1, 1, 1, so that's some vector like this. I'll put the A2 maybe here. So you have A1 and A2, and they span this plane. They span this plane in R3 that goes through the origin. And that's the column space of A. Right? And what's going on is you have this vector b, which is not in the column space of A, And that explains why, so you have some vector b like this, it's out here, it's not on the plane spanned by a1 and a2, so ax equals b has no solution. So let's just remind ourselves that the column space of A, is there a different color I can use? Nope, I guess. Yeah, maybe a green that's not as bright. Well, okay. So the column space of A is the span, okay. This is the span of A1 and A2. There we go. This looks a lot better. Column space of A. And remember that that's the collection of all possible A times X, right? If you take all the X's in R2 and then do A times X and see what results you get the vectors on this plane, the column space of A. It's the span of the columns of A. And since B is not in the span of the columns of A, there's no X such that AX equals B. Now what's the AX? Which AX? So the possible AXs are on this plane. Which AX will be closest to B, this blue vector B? Well, if you think about it, that is going to look something like, see, because you want the distance from B to the plane. So the distance from B to the plane is what you get by dropping a perpendicular. So it makes a 90-degree angle with the plane. And then this vector is going to be the AX that's as close to B as possible. And what is that vector? Do you remember what that vector is? So you have this vector B, okay? You have this subspace, in this case it's the column space of A, and you're looking for this vector, and this vector has the property that B minus this vector is perpendicular to the subspace. So what concept is that? What's this vector called? This vector here? It's the projection, right? It's the projection of B onto the column space of A. So that's going to be our A times X star. And so now we see one way to find X star. First, we can find the projection of B onto the column space and then solve for X star. So that leads us to one way to find X star is first, okay, why don't I move this over here? One way to find X star is to first find the projection of B onto the column space of A. And this is a good review for how to find that. We went over how to do this. One way to do this is to first find an orthonormal basis for the column space of A. And then once you find an orthonormal basis for the subspace that you're projecting onto, there's a formula for the projection. So first we need an orthonormal basis for the column space of A. And the column space of A is spanned by these two vectors, 1, 0, 0, and 1, 1, 1. So this was our A1 and A2. And we need to use these vectors to produce an orthonormal basis. Well, first of all, A1 is already perfect because A1 is a unit vector. So remember, first we need to find an orthogonal basis. So that was our W1, W2. Our W1 is just going to be A1. And our W2, that was what you get when you do W1 minus the projection of A2 onto W1. So the projection of A2 on W1, remember there's a formula, it's just A2 dot W1, so it's 111 dot W1, that's A1, that's 100, over W1 dot W1, W1. Okay. And this is equal to, well, this whole coefficient here ends up being equal to 1 because it's 1 over 1, that's 1. So you just get 1, 0, 0. And so therefore W2 is W1, that's A1. Hold on. Oh, sorry. It's this is not correct. It should be A2 minus the projection, right? Because what's going on, let's just remind ourselves. So you have A1 and then you have something like A2. You want to project A2 onto well, W1 or A1 and then subtract because you're trying to get this vector. Because you want that to be orthogonal to that. Okay, so it's W2 is equal to 111. That's A2 minus the projection, which is 1, 0, 0. So then you get 0, 1, 1. So that's our W2, and then what we need to do is we need to make this unit length, so we divide by the length, and we see that, so U2 is W2 divided by the length of W2, and W2 has length that's the square root of 2, right, because it's the square root of 0 squared plus 1 squared plus 1 squared. So that's the square root of 2, and so this is going to be, U2 is going to be 0, comma, 1 over root 2, 1 over root 2. So now we have our basis. U1 is 1, 0, 0. So remember U1, this is equal to U1 because A1 already has unit length. So you have U1 is 1, 0, 0, and then U2 is 0, 1 over root 2, 1 over root 2. That's our orthonormal basis for the column space of A, this set. And now we're ready to just use the formula. So step 2 is to find the projection of B onto the column space of A. Step 1 was find an, oh wait. Oh, we're still in step 1. Okay, fine. Step 1 was broken into 2 steps. Now we're ready to find the projection because the projection, remember the formula, the projection of B onto the span of U1 and U2, U1, U2 are orthonormal, so the projection of B onto the column space of A is just B dot U1, U1 plus B dot U2, U2. Okay, sometimes I'm drawing the arrows, sometimes I'm not drawing the arrows. I think the arrows are more of a distraction now, so I don't draw it as much. So anyway, that's the formula for projecting onto a subspace that is given by an orthonormal basis. And this is going to be, so B was 1, 2, 3. 1, 2, 3 dot 1, 0, 0 is 1. So you have 1 U1, so that's 1, 0, 0. And then plus B dot U2, so B was 1, 2, 3. So if you do 1, 2, 3 dot this vector, you're going to get 0 plus 2 over root 2 plus 3 over root 2. That's 5 over root 2. So 5 over root 2 u2, 0, 1 over root 2, 1 over root 2. And now we just need to add these vectors. You get 1, 0, 0 plus 0, 5 over 2, 5 over 2. That gives you the vector 1, comma 5 over 2, 5 over 2. So that's the projection of B onto the column space of A. This is the vector, just to remind ourselves, this is the vector in the column space of A that is closest to B. So this is our AX star, right? And we're trying to find X star. That's going to be our what's called a least square solution. It's the X that makes AX as close to B as possible. So now our next step is to solve for X star. And that's easy because we know what A is. A is this matrix, okay? And then we augment it with this vector, AX star. That's 1, 5 halves, 5 halves. And we need to solve for X star. So now we just use the row reduction, but you can actually see what the solution is going to be because this matrix times X star has to give you this. And so you see that the second component is going to be 5 over 2. And then the first component, well, the first component plus the second component times, the first component plus the second component has to equal 1. That's what this first equation tells you. So the first component has to be negative 3 over 2, because negative 3 over 2 plus 5 over 2 is 1. So that's going to be our X star. We just found what X star is. So that's called a least squares solution. To AX equals B. Notice that the least square solution is not even a solution to AX equals B, right? That's kind of the point. It's the X such that A times X is as close to B as possible. Okay. And what is this distance from AX to B? So let's just make this an aside. For this X star, the distance between AX star and B is so it's the length of, well, AX star was 1, 5 halves, 5 halves. B was 1, 2, 3. So you have the length of 0, negative 1 half, negative 1 half, and then that's the square root of 0 squared plus negative 1 half squared plus negative 1 half squared, and then that's equal to the square root of 1 half, which is 1 over root 2. So that's just an aside. But now you see why it's called a least square solution, because the sum of squares is minimized. Okay, well, that had nothing to do with the row space being orthogonal to the null space or anything, and I said that that would be part of this, and it is. It wasn't part of this first method, right? But I just went over one way to find. There's one way to find X star. This way has nothing to do with the row space being orthogonal to the null space. But the second way does, and it's going to lead to a formula. So another way to find x star is this. Let's go back to the picture here. So we saw that this ax star is going to be the projection of B onto the column space. Now what you notice about this vector here, the difference, that's B minus the projection, well, we can actually just write it as B minus A times x star. B minus A times x star has the property that it's orthogonal to the projection of B onto the column space of A. Right? This vector is orthogonal to this vector. But it's not just that. Because one of the facts is that when you have a vector, okay, and you project onto, so let me just write that down. So recall that when you project a vector, say V, when you project the vector V onto a subspace W, when you look at the difference, V minus the projection of V on W, this vector is actually not just orthogonal to the projection, it's orthogonal to all of W, meaning it's perpendicular to every vector in W. So for instance, in this picture, this vector, okay, it's not just orthogonal to this vector, it's actually orthogonal to every vector on this. It's orthogonal to the entire plane. Right? This vector is making a 90-degree angle with the plane. Okay, so maybe just a, okay, right? It's like if you have the xy plane and you have the z-axis, right? It makes a 90-degree angle with the entire plane, with all the vectors on the plane. And that's where this stuff I was talking about before comes in, because now we see that the projection, that this vector B minus A x star, right, this vector here is orthogonal to the column space of A. That's this green subspace. Well, now we see what this means. If you're orthogonal to the column space of A, okay, this is, remember this set, it's called the orthogonal complement of the column space of A. It's all the vectors that's orthogonal to the column space of A. Well, we have a vector that's orthogonal to the column space of A. Therefore, it must be in the null space of A transpose. Let's write that down. So it's in the null space of A transpose. And what that means is, now I'm going to go all the way back here, because I need space, that this vector B minus AX star, so this is in the null space of A transpose. And what that means is that A transpose times this vector must be what? It must be the zero vector, right? That's what the null space is. It's all the things that, when you multiply it by that matrix, go to zero. Okay. And now we can distribute the A transpose across. So this is going to be A transpose times B minus A transpose AX star is the zero vector. And now if you just add A transpose AX star to both sides, you get A transpose AX star equals A transpose B. Okay, so you add this to both, you add A transpose AX star to both sides, and then you just rewrite. You know, you just switch the order in which you're saying that the two things are equal, and then you get this. And if X star satisfies this equation, then B minus AX star will be in the null space of A transpose. So it will be orthogonal to the column space of A. And that means that AX star will be in the, hold on, let me think about this. See, what we did is we showed that X star has this property that's in the box. But how do we know that if X star has this property in the box, that it must, give you this configuration? The reason is because you can reverse the order. So if X star satisfies this equation, then B minus AX star is in the null space of A transpose, which means that it's orthogonal to the column space of A. One thing that I think I'm sort of sweeping under the rug is that when you have a situation like this, there's only one way to decompose B as a sum of a vector that's in your subspace W and a vector that's orthogonal to W. So it's not just that it's possible to do it, it's that there's only one way to do it. I'm not sure if I proved that in I probably didn't prove this because it's a more advanced theorem. But it's true that there's only one way to decompose B into a vector that's on this subspace plus a vector that's orthogonal to the subspace. And since we were able to decompose this vector has to be the projection. Okay? So, yeah. So that explains why if X star satisfies this equation, then AX star has to be the projection of B onto the column space. Okay, and this equation is called the normal equation, or the normal equations. If you think about this as a matrix times vector equation, right, it's really it's a simultaneous equation. And notice that if A transpose A is invertible, then we can multiply both sides on the left by A transpose A inverse, and then we get that X star is A transpose A inverse A transpose B. So with that, let's go back and solve this least square solution using this formula. So we need to find, so in this example, A transpose A is this matrix times this matrix. And when you calculate it, you get this matrix. And we can find A transpose B. That's going to be this matrix times B. And this is going to be 1, 6. And now we need to solve A transpose AX equals A transpose B. So we can just set up the augmented matrix and then solve. Another thing you could do is you could find the inverse of this matrix and then multiply it by this vector. That's also fine. But we might as well just solve the system like this. It's probably a little bit faster. So I'm going to switch I'm going to replace row 2 by row 2 minus row 1 to get a 0 here. So I get this, and then I need to divide row 2 by 2, So I get this. And then replace row 1 by row 1 minus row 2. And I get this. And this is the same thing we had before. We get x star is equal to negative 3 halves, 5 halves. So that's the least square solution. All right, so more than one way to do this. And there's, if you use a programming software, like or programming language, if you use Python, you can find the least square solution pretty easily. And one thing to note is that in this example, there was only one value of x star, but if the columns of A were linearly dependent, then there will actually be more than one x star. There will be one ax star, because this was the projection of B onto the column space of A, right? But there's going to be, since A has linearly dependent columns, right, there's going to be lots of different x stars that give you the same ax star, right? You're solving the system ax equals the projection of B onto C of A. I mean, if you just call this vector, if you call this projection like y, then you're solving ax equals y, and this is a consistent system. It has a solution, but if A has linearly dependent columns, it'll have infinitely many solutions. So there will be infinitely many x stars that work. Okay. And then those would all be called least square solutions. Okay. And there's more to say about that, because now you can think about, well, out of all the possible x stars, which one is the quote-unquote best x star? Like, out of all the possible x stars, which one of those has the smallest length? Right, that's a different type of thing. And then that leads to more theory. There's something called the pseudo-inverse, and that kind of picks out that particular quote-unquote best x star. It's the smallest length out of all the possible x stars. Okay, so that was the method of least square solution. And then in the next video, we're going to apply this to find the best fit line. If you have a set of data points and you want to find what's the best fitting line, there might not be a line that goes through all the data points, but in some sense, the best fitting one, we can use least squares to solve that. So that's what we'll talk about next time. And now one more thing maybe I should add before I stop the video is that if B itself was in the column space of A, then the solutions to Ax equals B would just be the least square solutions, right? The distance would be 0. Okay. Okay, thanks.